So for number 30, it's telling us that the linear combinations of the vector v and w, they fill the plane unless, and so for two vectors to fill a plane, they must be linearly independent. That is, suppose that this is vector v, and this is vector w. So in this case, we can go anywhere in the plane by putting CV plus dw and varying the constant c and d. However, if v and w, they are on the same line, so suppose that this is v and suppose that this over here is w, then no matter how you add them, you're always going to be stuck on this line. You are not going to have any components that let you get, say, here or here or here. You're basically just going to be stuck on that line forever. So they fill the same plane unless they are collinear. Okay. And now they want us to find four vectors u, v, w, z with four components each so that their combinations produce all vectors in four-dimensional space. So we want to produce four vectors that are linearly independent, so each vector adds in a new dimensional information. So what I'm going to do here is I'm going to say that u is going to be, it's going to have the component of the first dimension. V is going to have the component of the second dimension. Let's see, UV, W is going to have the component of the third dimension. And Z is going to have the component of the fourth dimension, 0, 0, 0, 1. Yeah. So when we combine these, we can see that we have information about the first dimension, the second, the third, and the fourth. So that means that we can access anywhere that we want in 4D space, right? And so that is it for number 30. So what we just did here was that we saw that in 2 dimensions, we need to access 2D space. They need to be linearly independent, so not on the same line. And to access 4D space, the four vectors need to be linearly independent. So this is a pretty easy way to guarantee that they're not combinations of each other. And that is it for number 30.